H.2 Introduction to Quicksort. In this part, we will study another new sorting algorithm. So the problem, it's an old problem, so we just revisit our problem number 4. Why we do another new sorting algorithm? There is some important reason behind it. Here, the main reason we emphasize overall performance. That is our main focus. We know for a sorting algorithm to be useful in the real-world applications, the overall performance is the most important. So what do you mean the overall performance? Here, I think we talked about that before. In general, in the general situation, the overall performance refers to the average case performance, right? Average case. Not best case, not worst case, average case. Here you can see for the sorting algorithms we have learned so far, none of them has really good overall performance. Selection sort, bubble sort, insertion sort, and merge sort. The overall performance still not the best. There is a lot of room to be improved. So you can see for different sorting algorithm, there is some special property. Some sorting algorithm is good at this particular property and some different property. For example, insertion sort. Insertion sort has a nice property. It has good performance for almost sorted array. Almost sorted array. Very special. Merge sort. Merge sort has another property. Nice property. Its worst case is not very bad. Worst case is pretty good. For the merge sort. So let's recall the merge sort a little bit. What is its most important property? Its worst case efficiency, big O of n log n. N log n. That's really good. N log n. So if you want to use some sorting algorithm whose worst case is under control, not very bad, worst case, pretty close to the average case, well under control, then you should choose the merge sort. But now our focus is different. Our focus, we don't need this property, okay? We don't need that property. We want to have the best possible average case efficiency. All right, so now you understand we need to develop some new sorting algorithm. All right, so let's look at the idea. We use the divide and conquer approach. But how do we use it? That is an issue. How do we use it? Okay, here we want to look at that details. First, we know the goal, make the overall performance as fast as possible. But that goal is pretty abstract, right? Pretty abstract. How do you achieve that goal? That's not easy. Okay. So basically, when we develop a new sorting algorithm, we try to use some new way to solve the problem. But after we get a new solution, then we do experiment. only after we do the experiments, then we can compare which one has the best overall performance. Without doing experiments, it is not easy to see which one has the best overall performance. So for that reason, in our project number 2, so I will give you quickly, probably this weekend, I will assign it. Do experiments on this new sorting algorithm, the Quicksort. All right. In order to get the best average case performance, okay, we can sacrifice a little bit. So you have to take some cost, the cost at the worst case, tolerate poor worst case performance. How poor? So we know usually the worst case n square category. For selection sort, bubble sort, insertion sort, the worst case in this category. So we also expect we may have this kind of worst case, but we can tolerate it. All right. The reason we can tolerate, because the probability for the worst case is very low. So you look at the worst case happen, the percentage extremely small. When you run 1 million times, less than 1% of times, you may get a worst case, less than 1%. That probability is very low, so we can tolerate that. So with that kind of mental preparation, now we are ready to work on, just get some idea first. At the early stage, we need to have some idea. All right. So we need to do some analysis. The analysis should be based on our current experience. Based on our experience. More specifically, based on our experience from the merge sort. Change view on divide and conquer. So let's look, how do we do divide and conquer on the merge sort? Okay, then we try to change the view. To get a new solution, you need to use some new view on it. All right. So first, we need to know what view do we use on the merge sort. Then we can do the change, right? So here, let me draw this chart to look at the merge sort first. For the merge sort, divide and conquer, we have 3 steps, right? Divide step, conquer step, combine step. First, the conquer step, basically we just do recursion. That means we do not need to really do anything different. Recursive function calls. Okay? So let's go to the other 2 steps, divide step and conquer step. For the merge sort divide step, so easy. Cut in the middle. Separate 2 subarrays from the middle location. Okay? Near the middle. Okay? Precisely. That's so easy. The cost is only big theta of 1. Okay? Then combine. Then it is hard to combine the merge step, right? We need to do a lot of comparisons to merge 2 sorted arrays. Okay? So when we do that, you can easily see the cost is big theta of k. What is the k? Right? The k, current data size. Data size, total size. Total number of elements from both subarrays. That's the data size. So big theta of k. All right. Now, we can go to the new idea. Yeah. So we don't want to do the same thing as the merge sort. Otherwise, you just get the same solution. Yeah. So we want to have some completely different solution. Yeah. So when we do that, let's take the opposite way. Opposite way here. We want to make the combined step as easy as possible. Big theta of 1. Yeah. The lowest possible cost to combine two sorted arrays. How can that be possible, right? How can you do that? Yeah, we will see later. Yeah. Here, we just want to know what direction we want to go. We want to go this direction. This direction, we want to make the combined step as easy as possible. That's it. Okay. Then you have to pay a little more on the last step, divide step. Okay. You have to pay more. Yeah. So we pay big theta of k to divide, to separate our data into two subarrays. Okay. So you can see, at least we get a new, different view on this problem. It should be a new solution. Is this solution better or worse? We don't know. Okay. So after we solve the problem, then we do experiments, compare this new sorting algorithm with other known sorting algorithms. Then, using the experiment data, finally, we can see if it is the best or not. Yeah. All right. Next, we will try to implement this idea, and we call this new sorting algorithm the Quicksort. Why it is called Quicksort? Yeah. People just call it because after those people did experiments, the overall performance, extremely good. Yeah. It beats almost all other known sorting algorithms. Yeah. 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 You know, so that for that reason, it deserves this name, Quicksort. Yeah. From this name, it's supposed to be overall quick, right? Overall quick. Yeah. Yeah. All right. Yeah. So let's go to the implementation details. Yeah. All right. The first question. How to make combined step easy? That may not be trivial. That may not be trivial. How do you make combined step easy? So we need to do some analysis to see that. Combined step. Yeah. Here, I need to use some diagram to show you what do we really need to do in this step. Yeah. What do you mean easy here, right? What do you mean easy here? Big theta of 1, right? Yeah. Specifically, big theta of 1. Yeah. So we translate in this way. Almost do nothing in the combined step. Almost do nothing. You do something. You do the minimum, right? The minimum one. This one is what you need to do. Minimum. Huh? After that, done. Combine. Okay. Combine two sorted arrays to form a new, bigger sorted array. Yeah, done. How can that possible? So let's see some analysis. The first array, A array. Yeah. Second array, B array. Yeah. All right. Excuse me. Now, all right. So now, two separated subarrays. Yeah. All right. Before conquer step. Yeah. So there is a conquer step. Recursive call to conquer it. Yeah. Before conquer, The first array not sorted. Second array also not sorted. Okay, all right. Then conquer. Recursive call. Yeah, conquer each one. Yeah. First array sorted. Second array also sorted by recursion. All right. After that, we want to combine. Okay, put together to get a new, bigger sorted array. Okay, yeah. What do? We just put together. Okay, yeah. We just concatenate. I like to use this word, concatenate these two subarrays. Yeah, the whole array, we just put them together. The whole array automatically sorted. In general, it's not true, right? In general, it's not true. But if we do something very special, we enforce some very special condition, it is possible. The question is what kind of condition you want to enforce, right? What kind of condition you want to enforce? That condition is very special. So we need to find that special condition. If we have that, then we have this property. So you put them together, automatically sort it. Almost do nothing, right? Yeah. In that way, this merge step, very cheap. Yeah, very cheap. Yeah, the cost very low. Yeah. All right. So now the goal, yeah. After conquer, when combine, do nothing. Or almost do nothing. Yeah. Because you still need to do that one, right? If you argue, still need to do that one. Very little. Yeah. Yeah. So we can say almost do nothing. Yeah. Yeah. But here I just want to save some space. So I put do nothing. Okay. Yeah. All right. Now that condition, we really need to find it. So what condition we really need to support this property? This is a special property, but we need some condition to support it. So can you imagine that based on our analysis so far? Can you imagine that special condition we really need for this step? Yeah. That condition is not very complicated, but pretty straightforward. Let me write here. A of I, the value of any element in A array is less than or equal to the value of any element in B array. That condition. How special it is. Okay? Or in other words, the maximum value in A array is less than or equal to the minimum value in B array. Think about if you have this property, then you put two sorted arrays together. Are they, the whole thing, the whole array automatically sorted? You can imagine, yes. Because the maximum is still less than or equal to the minimum in the other one. Yeah. These two already sorted. You put them together, sorted. Very natural, right? So that observation, although very simple, but it's so critical for this new sorting algorithm. So critical. Yeah. Next questions. How can you make that happen, right? How can you make this condition true? That's not easy. That's not easy. Yeah. So this condition is in our wish list. We have not had it. We need to do a lot of effort. We need to remember that big theta of k, right? We need to pay this much to get this condition. Okay, so that's the cost we need to do in the devise step. Yeah. We need to do a lot of things in this devise step. Yeah. So the next question, how to do it, right? Yeah. All right. So before we go to the next step, so let me summarize a little bit. Yeah. We went through long analysis path. So now I want to summarize a little bit. Okay. Most important step divide step. If we can do the way that satisfies this desired condition, we almost done. Yeah, we almost get our final solution. Okay, yeah. Requirement. How to split the array into two subarrays, A subarray, B subarray, such that critical condition. The value of any element in A array is less than or equal to the value of any element in B array. That's simple. That's the condition. How to get that? That's not easy. Our next video, we will do that. In our next video, we will solve that problem. Still, we need to do a lot of things to get there. Yeah. For this video, we only need to know what do we want to do. Here, we know it. We want to get this condition. We are willing to pay this much cost to get this condition. That's enough. Okay? Yeah. All right. One thing you need to know, even after we get this condition, we do not require A array sorted, B array sorted. We do not require that. We just want to separate two subarrays. The values in each subarray, when we look at them together, satisfy this critical condition. Sorting each subarray, we leave to the conquer step. Recursive function calls. Yeah, so we don't worry about that step. Okay? Yeah. Conquer step, we don't worry about that. Recursion automatically. Yeah. All right. So this is our first video. Yeah. All right. The story. Yeah. The whole getting started of this new sorting algorithm. The story behind it. Yeah. All right. So let me stop here. Yeah.